assumption that we have to apply in order to get the air standard cycle. These are called as the air standard assumption. The working fluid is air, and then we have the process of heat up and rejecting of heat is done externally. Okay, and every processes are made up of a reversible, reversible processes. And then the cool air standard assumption is to get all the value, the Cp, the Cv at 25 degrees C. So that is mentioned, and we have looked before this. And then we have looked at the Otto cycle. This is our Otto cycle. Okay, this is Otto cycle, whereby we have for Otto cycle, we have the compression process from 1 to 2, and then we have heat addition process 2 to 3, and then we have expansion process 3 to 4, and we have rejection process 4 to 1. The compression 1, 2 and expansion process 3, 4, we assume that the processes is done isentropically, or also known as the reversible adiabatic process. Okay, and then the heat rejection and heat addition is done as isochoric or constant volume process. Okay, and then if we can sketch the process on a PV diagram, this will look like for the Otto cycle. So this Otto cycle, or the cycle area that we have from this air standard assumption, or from this air standard cycle, we try to convert, right, the area which represent the W net as a rectangle shape type of a diagram. And based on this rectangle shape of the diagram, which represent equal to the W net, the area, then the pressure that we read right here is called as the mean effective pressure. And the uses of mean effective pressure is purposely is to compare between two same capacity of engine. Like I mentioned before, if you want to compare which one have a better work output, then we look at the MEP. The higher MEP, okay, for the same capacity of engine is better because it will produce more W net. Okay, more W net. And we can prove that for air standard cycle, for Otto, we can prove that the thermal efficiency is a function of what is being called as the compression ratio. The compression ratio is R value. What is R? R value is the maximum volume divided by the minimum volume, right? And in this case, for an Otto cycle, what is the maximum volume? The maximum volume consists of the clearance volume plus with the swept volume. And what is the minimum volume? The minimum volume is at TDC, which is the VC, or the clearance volume. But as I have discussed before, the R value is always constrained by the time of fuel being used. Although that we can see if we increase the compression ratio, we might increase the thermal efficiency, or the thermal efficiency of, in this case, the Otto cycle. But that is not as easy as that. It's all depend on the ignition temperature or the flame temperature of the combustion of the fuel. That will restrict the value of compression ratio. Because if we get too high compression ratio, we might have a phenomena called knocking, okay, engine knocking, which will damage our engine. So we must have a limit of R value, either for Otto cycle, which represent the spark ignition engine, or also known as the petrol engine. Okay, which engine has spark plug, that is called as the spark ignition engine, right? And then we have looked also the analysis or example of Otto cycle. This is what we have discussed before, the problem 5.5 from our textbook. Okay, and the first part of this exercise, what we have looked is to see what is the equation of states, the ideal gas equation of state for each state 1, 2, 3, and 4. So this is what is being given as the equation of states. And then after that, we have looked to the equation for a given process. This is the equation for a given process. Then we have looked at process 1 to 2, what we have, and then all the equation involved. And then we have looked at the process of 2 to 3. This is process of 2 to 3. What equation we could write. And then we have the equation for 3 to 4. Where is 3 to 4? Yeah, this is 3 to 4. Okay, this is 3 to 4. And then lastly, we had the equation for a given process as 4 to 1. And this is 4 to 1. And then from there, we also look at the what is being called as the pressure ratio. Okay, the pressure ratio. The pressure ratio is can be written as the maximum pressure divided by the minimum pressure. In this case, it's P3 divided by P1, which is equal to P3 over P2 multiplied by P2 over P1. This is the relationship between the overall pressure ratio and also the pressure ratio from process 1 to 2 and also process 2 to 3. Okay, so we have looked at this solution, and I have given the, okay, we haven't finished everything for the question, but I have given the guide how to get the answer for this given, or for the case of this to get the pressure ratio between P3 and P1. I think that is where we have stopped from the last meeting. Okay, from the last meeting. So now what we are going to do is we are going to continue with problem 5.6, which still involving the Otto cycle, but with different representation of the analysis or the problem for this one. So let us read together the question. A 4-cylinder petrol engine has swept volume of 2,000 centimeter cube, and the clearance volume in each cylinder is 60 centimeter cubic. Calculate the air standard cycle efficiency if the introduction condition are 1 bar and 24 degrees C, and the maximum temperature is 1,400. Calculate the mean effective pressure based on the air standard cycle. Okay, so this is the problem, and can we try to look at the geometry of this type of engine by sketching the piston and cylinder. All right, so we have an engine which consists of 4-cylinder, and it's been said that the 4-cylinder have this total of swept volume, which is 2,000 centimeter cube. So if you look at one cylinder, so this should be our TDC, and this should be our level of DDC. So if we look at one cylinder, then the red color should be our VC. This is the volume of VC, which is given as 60 centimeter cube. Because the question tells us that the clearance volume of each cylinder. But this volume is based on the 4 cylinder. Meaning that if we look at the swept volume right here, the swept volume for 1 cylinder is equal to 2000 divided by 4, which is 500 cc. This should be our Vs for 1 cylinder only. So this is our Vs for 1 cylinder. Okay. And then we are going to calculate what is the air standard efficiency. Then we know that for Otto cycle, 4-cylinder petrol engine represent the air standard cycle for a petrol engine represented by Otto cycle. Okay. If gas engine also, if we have gas engine, let's say we use a CNG or we use LPG, the gas engine also for air standard cycle for gas engine is also referred to Otto cycle, right? As long as the engine have spark plug to initiate the combustion process, then it should use the air standard cycle as Otto cycle, right? So to calculate the air standard cycle efficiency, then what we got to do is to look at the Otto cycle thermal efficiency. This is the thermal efficiency for Otto cycle, which is a function of compression ratio, which is 1 minus 1 over R K minus 1 or gamma minus 1. Okay, gamma is equal to K, which is equal to the Cp divided by Cv. So we need to get what is the R value. What is the R value? The R value is the V max divided by the V min. What is our V max? The V max consists of Vc plus Vs. And what is the V min? The V min should be our Vc. Okay, so what we have right here is 500 plus 60 divided by 60. So how much is that? Five 60 divided by 60. Yes, how much is that?
9.33.
9.33. 9.333. Therefore, our thermal efficiency for Otto cycle is equal to 1 minus 1 divided by 9.333. The K value for air is 1.4 minus 1 is 0.4. This is equal to it should be 59, 0.591 or 59.1%. Correct? Is that the correct one?
Yes, okay.
All right. Then next we go for the introduction condition of air. If the introduction condition are 1 bar, 24 degrees C, and the maximum cycle temperature is 1400, calculate the mean effective pressure based on the standard cycle. So in this case, what we have to do is we have to get the what is the W net? Okay, what is the W net? Because we know that what is MEP. Basically, if we can sketch what is MEP, this is P, this is V, right? If this is our Otto cycle, what is basically MEP? So we have this is W net. And what is MEP? The MEP is we represent the area of W net as a rectangle. So this is our rectangle. This is equivalent to W net also. Okay, the area is equal. So the height of this rectangle, the pressure represented by this height of the rectangle is called as the MEP, mean effective pressure. Then of course we need to analyze the cycle. So we know that this is the introduction or the induction condition 1. This is the compression 2. This is the heat ignition 2 to 3, and 3 to 4 is the expansion process, and 4 to 1 is the heat rejection process. So this is our heat supply Q23. This is our heat rejection, which is Q41. And this is our compression process, where we have input of power or work, which represent as W12, and this is the work output, the expansion process, which represent W34, the positive work. W12 is the negative work. Q23 is the positive heat transfer, and then Q41 is the negative heat transfer because it's ejection. And if we look at this parameter given or the properties given, the 1 bar is referring as the P1. This is 1 bar. And then the 24 degrees C, what is in Kelvin? 24 plus 273. What is that? 301. No, 297. And the T1 we convert to degree C, to Kelvin, sorry. This will present 3297. 297 K. And the maximum cycle temperature, cycle temperature is always referring the state after the heat addition process, which is T3. So the T max in this case should be equal to T3, and given as 1400, which is equivalent to 1673 Kelvin. Everything should convert in Kelvin because we might use the ideal gas equation of state, PV equal to MRT. Then we need to use in Kelvin. If we are going to get the delta T, it's no problem. The delta T in Kelvin and delta T in Celsius is equal. Okay. So how to get the MEP? Then the MEP, this is our VS. Okay, this is our VS. So in order to get, we know that the pressure time volume is W net, then the MEP is equal to W net divided by VS. So MEP, the equation of MEP is equal to W net divided by VS. We already have the VS. Remember, this cycle, okay, this PV cycle, the Otto cycle that we have sketched right here is basically for one cylinder. Okay, for one cylinder. So that's why right here we use the VS value as 500. Okay, so how to get the W net? We know what is our thermal efficiency. What is the definition of thermal efficiency? This is equal to the W net divided by the Q in, which is the Q23. Okay, Q23. So from here, we know what is our thermal efficiency. We have got it, 0.591. And then now we got to solve for the Q23. in order to get the W net. So what is Q23? The Q23 is basically based on our process 2 to 3. Then we are going to have this as CV T3 minus T2. This equation we get from the equation from the first law of thermodynamic for closed system, whereby the W23 is equal to 0. So what's left is just Q23 equal to T3 minus T2, where the CVT is the internal energy. Okay, the internal changes of internal energy. And in this case, we got what is the T3, the CV we are going to use for air. Then we need to define what is our T2. T2 is equal to T1. Okay, guys, advise me. V divided by V, K minus 1 or 1 minus K. And this should be equal to T1, 1 over R or R. Come on, guys. Guys? Hello?
R, sir?
Yeah? R, V1 over V2. No, I'm asking you all. Which V divided by which V?
V1 over V2.
V1 over V2. Sorry. This is V1 over V2. What is V1? The V1 is V max, correct? What is V2? V2 is V min. So V max over V min is equal to R value. Okay, so get what is your T2? T1 is 297. Your R value is 9.333. 9.333, 0.4. Is this one correct? K minus 1?
Yes.
Okay, so what is your
Yes,
T2?
sir.
What is your T2?
Seven two 5.7.
7.7
5.7.
Kelvin.
Okay.
Okay, so calculate your what is your your Q23. This is a 0.18. T3 is a 1673 minus 725.7. So what is your Q23?
One 7.333. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333. 0.4. 1 7.333 680.16.
1
680.16.
kilojoule. Kilojoule or kilojoule per kilogram? Guys, kilojoule or kilojoule per kilogram? Kilojoule or kilojoule per kilogram?
Kilojoule per kilogram.
Yes, because the CV is in kilojoule over kilogram Kelvin. So you must have kilojoule over kilogram. And then from here, you will get what is your W net. What is the W net? The W net is thermal efficiency multiplied by the Q23. The thermal efficiency is 0.591 multiplied by your Q in. Q23 is 680.16. So what is that? Anyone?
401.97.
401.97.
1.97.
Ya ke? Why I got 406? 591 multiplied by 680.16. Okay, thank you. That's right. 402. Okay. Kilojoule over kilogram. Now we could get what is the MEP. So the MEP W net divided by WS. So the MEP equal to W net, which is 402.0 divided by the VS. The VS is 500. Look at the unit. So what is a kilojoule? Kilojoule is a kilonewton meter divided by kilogram. Right? Or what is kilonewton meter? Anyone? So right now, what we have here is a kilonewton meter divided by kilogram. This is for the W net. What is Newton? Newton is equal to kilogram multiplied by meter over second squared. That is Newton. Right? And then we know that the 500 is in centimeter cubic. Okay, now we have to convert as Newton. This is a centimeter. We want to cancel the centimeter. We have meter. So this should be 100. And we want to cube it. So this is cube. This is cube. Then this become 6. Okay, so we look at all the unit right here. This is meter cube. Meter. Meter. Where's one more meter? Newton, is that right? Undo first, undo. Okay. Kilonewton meter. Newton is kilogram meter second square. kilogram. I need the unit of meter squared at the bottom. What did I do wrong? Anyone? Kilonewton meter is kilojoule. Okay, this I convert already. Kilogram, okay. Centimeter. I need to get the bottom part as meter squared. Anybody can see where did I do wrong? Guys? Kilojoule is kilonewton meter. Yeah, kilojoule, right? And oh, sorry, I need. What do I do? Okay, let me do it again. I need Newton over meter, so I need to maintain the Newton. I don't need to cancel off the Newton because we know that the pressure is Newton over meter squared. Okay, let me do it again. Okay, please check together with me. What is 402? 402 is a kilonewton meter, which is represented as kilojoule divided by kilogram. Multiply by our 500 is 1 over centimeter cube. Multiply by, this is centimeter, this is meter, this is 10 power of 6 cube. This now is right. So I can cancel this meter cube becoming 2. This is meter, this kilogram. Hey, what happened to the kilogram?
So the newtons.
Pardon?
We haven't cancelled it.
Tak dengar.
Newton, so we haven't cancelled it.
Cancel with? Sorry. Ni cancel. Kilo Newton. Oh, this is kilogram. Why did I do wrong? Oh, I see. Sorry guys. I think this one Q23 is CV T3 minus T2. You see right here. We need to get the M value. Okay, we need to get the M value because this is in kilojoule or kilogram. So we need the M value. So how to get the M value, guys? So basically, we are going to get the M value is from the M is equal to PV divided by RT. We are going to get 1, 1, 1. Okay, what is V1? P1 is 1 bar. Convert to kilo. V1 is equal to Vs plus Vc, right? The V1. Vs plus Vc is 500 plus 60. R for air is 0.287. T1 is 297. So we need to convert this centimeter to meter. So they have centimeter cubic multiplied by centimeter cubic 10 power of 6 meter cube. Then we have the m value. Okay, can you guys get for me what is the m value? Okay, anybody?
Zero point zero zero zero. Another zero.
Okay.
657.
Wow. Okay. And then this value we need to divide, or you need to multiply everything in kilogram. So we need to multiply by 0.0, multiply or divide, sorry. This is MEP. 400. This is a kilojoule over kilogram. Wow, what did I do wrong, guys? Okay, kilojoule over kilogram, CV, that's right. This is in WNet, is in 402. So the MEP right here, we left the MEP right here, we left kilogram. So this is 10 power of 10 power of we use V squared. If we use V times the WNet is, oh lama. Okay, guys. Sorry, guys. Sorry. You know what is MEP, right? The MEP is basically is a V times V. This is pressure. So when pressure times by volume, you got in kilojoule. It's not kilojoule per kilogram. Okay, this is in kilojoule. If you look per cycle, okay, per cycle. So we don't have any kilogram right here. All right, so let us look first. Okay, I will try to relate with using the V. Okay, let us look dia punya nilai V dia punya WNet. In this case, the WNet is equal to the MEP multiplied by the VS. Okay, and in this case, the VS is in let's say is meter cube, and the pressure right here is in say is kilonewton over meter squared, which is kPa. Then what is we have right here is a kilonewton over meter squared multiplied by meter cube. Then we have kilojoule. That's right. So don't have to multiply by the value of a kilogram. Okay. So what we have here, we need to convert to bar. Okay. So this one, we need to convert to bar. Because the answer is in bar. So how to get in bar? Divide by, this is meter, meter, centimeter, centimeter. What we have here is basically is equal to kilonewton over meter square. Give me the value, guys. Give me the value of this. This 402 divided by 500 multiplied by 10 power of 6. What is that value?
So dapat 804
804
000.
000.
Yes.
And the units now is in kilonewton, right?
Yes.
Meter square. Oh. It's not right, eh? Kalau kita nak convert pada bar, ini is bar. 1 bar is 100 kPa. Pun tak betul juga ni. Aduh. This is kPa, this is kPa. 800 dapat 8 bar. 8.04 bar. What is the answer? 5.28. Anyone can detect what is wrong in my solution right here? MEP this is Vs, is correct. This is Vs. Vs is 500. 4,000 divided by 4, 500. W net, the W net MEP, okay, the W net is equal to the thermal efficiency. The W net is equal to W net thermal efficiency, W net divided by Q23. The thermal efficiency is correct. 591. Anybody can detect what is the error right here? Anyone? Boleh detect tak? Kalau detect tekan IV dulu. Let me see after this. Let me look at the solution. Okay? But basically this is what we should have. But it's not right, it's wrong. Okay. IKIV first this problem. Let me look after this and see what is the right solution. Okay, any question, guys? Any question? Right. If no question, what we are going to do right now is to look at the second air standard cycle. The second air standard cycle, which represent the CI engine. So this is our CI engine. Okay, this is our CI engine. And the CI engine represent the air standard cycle for the diesel engine. Okay. In diesel engine, comparing diesel engine and petrol engine, this is what we have. In the petrol engine, we have a spark plug. But in diesel engine, what we have is a fuel injector. So this is the fuel injector. And how do we get the ignition is basically because of the high compression process. When the temperature of the compression or the air compressed is higher than the ignition or the flame temperature of the fuel, then automatically it will be auto ignition. Okay, so we need a very high compression ratio. So in this case, a typical for SI engine, the value of compression ratio is about 24, while in SI engine is only 12. So we know that the compression ratio can represent the final pressure after the compression and also during the combustion process. That's why we can see that the compression ignition engine can produce more power compared to the spark ignition engine. That's why we have the application of diesel engine usually is in heavy vehicle, in trucks, trailers, buses. Usually they use compression ignition engine, whereby the diesel as the fuel. Okay, so in this air standard cycle for diesel, we have compression process, which is 1 to 2. This is the process from 1 to 2, the isentropic compression process. And the V2, the V1 divided by 2 is also the same as known as the compression ratio. And then we can see here the heat addition process. Okay, the heat addition process 2 to 3 is basically done at constant pressure. If for Otto cycle is done at isochoric or constant volume, but for diesel cycle, we are having the heat addition during or the process basically follow as P equal to constant. So the P3 is equal to the P2. And then after that, we have the expansion process 3 to 4. And again, we have the heat reaction process 4 to 1, the same as the Otto cycle is done during isochoric process. Okay, so 1 to 2 isentropic compression, 2 to 3 constant, 2 to 3 is a constant. Oh, this is not right. Ini bukan constant volume heat addition, but this is a constant pressure heat addition. So please, betulkan. This should be 2 to 3 is a constant pressure heat addition. 3 to 4, still the expansion process, isentropic, reversible adiabatic, and 4 to 1 is the heat rejection. So this is how the PV diagram look like for the diesel engine or the diesel air standard cycle. Okay, and from this cycle, the analysis, we can look in terms of the heat addition, in terms of the heat rejection, in terms of the work input, and also the work output. So 2 to 3 heat input, 4 to 1 heat output, and then 1 to 2 is the energy in terms of work transfer input, and 3 to 4 is the work output. So if we look at the definition of our thermal efficiency, before that, we are going to look at the process of 2 to 3. Basically, based on the closed system, right? The closed system equation, the energy balance, what we could have from 2 to 3, the energy in plus the energy transfer in equal to the final energy plus the energy transfer out. Then we have this equation for the first law of thermodynamic. Okay, so the final equation for Q in this case, we are going to combine the boundary work and also the enthalpy. So this is the combination of the boundary work and the internal energy. Sorry, the internal energy. This is boundary work, internal energy, and we know that the U plus PV is equal to enthalpy. Then this will finalize for the Q in process as the Cp T3 minus T2. And we have another parameter apart from the compression ratio. We also have what is being called as the cut-off ratio. And what is the cut-off ratio definition? The cut-off ratio is the ratio during the heat addition process. Okay, so this is given as the RC, representing the cut-off ratio, V3 divided by V2. Okay, V3 divided by V2. And this is also equivalent to as the specific volume or the specific volume, V3 over V2. So by definition, we can write here what is the thermal efficiency of the diesel air standard cycle, which is the W net divided by Q in. And this is equal to 1 minus Q out over Q in. And we can prove that based on this substitution of the T1, T4, T3, and T2, we can prove that the final equation for this air standard cycle diesel engine is given as 1 divided by RK minus 1 multiplied by RK cut-off ratio, power of K minus 1 divided by K multiplied by cut-off ratio minus 1. Okay, the K value is again is the Cp divided by Cv. The R value is V1 divided by V2, and the RC is V3 divided by V2. From this equation, you want to get this type of proving in the red color, I think you need about 2 pages. Okay, 2 pages. So you can have a try, no problem, and try to prove this equation, but it's quite tedious. Basically, you have to substitute the temperature in terms of your cut-off ratio and also the compression ratio. Okay, and when we compare the thermal efficiency, right, in this is in the real case. If we compare the compression ratio by this equation, we could have that the Otto cycle have a better thermal efficiency compared with the diesel cycle. But if we could look at the same compression ratio, the same value of R, okay, the same value of R. But actually, as far as the power is concerned, because of the compression ratio of the diesel engine is greater than the compression ratio of the Otto engine, then what we could have in terms of power, the diesel engine will produce more power compared to the Otto engine. In other words, diesel engine can produce more power compared to petrol engine. Okay, that's why like I said just now, because of the high compression ratio, we get a high pressure ratio, then we could have more power output or more higher value of torque. That's why we can see that usually for diesel engine, it's not for fast moving vehicle, but it's used for a very high payload type of engine, okay, because it can cope with the higher value of payload. Okay, so that is for our diesel engine. So let us look at the one question regarding of the diesel cycle. Problem 5.7. This is for diesel cycle. Calculate the cycle efficiency and mean effective pressure of an air standard diesel cycle with compression ratio of 15 and maximum and minimum cycle temperature of 1650 and 15 degrees C respectively. The maximum cycle pressure is 45 bar. So what we have to do right here is to get the sketches of the engine of the cycle for diesel. So let me do it on top of this question. The diesel air standard cycle, this is P, this is V. Okay, this is our cut-off ratio. And this is the expansion process. And this is the compression process. Okay, this is 1, this is 2, this is 3, and this is our P2, which is equal to the P3. Okay, this is 4. And we know that both expansion and compression will follow PV power of K equal to constant. This is V4 equal to V1 isochoric. The compression ratio 15:1. What is compression ratio? Compression ratio is a V1 divided by V2, which is equal to 15. And then the maximum and minimum cycle temperature. The maximum cycle temperature should be T3, which is the temperature after heat addition process. So this is 1650 plus 273 is equal to 1923. 1923 Kelvin. And the minimum should be the intake or the beginning of the compression temperature, which is T1. T1 is equal to 15. So 15 plus 273 to 88 Kelvin. Okay. And the maximum cycle pressure is 45 bar, the maximum cycle temperature pressure, where the maximum cycle pressure should be right here, which is P2 equal to P3. P2 is equal to P3, which is equal to 45 bar. Okay. So what we have to do is to get the calculate the cycle efficiency and the mean effective pressure. So where is our mean effective pressure? This should be our mean effective pressure. Okay. So this should be our W net. And this W net should be equal to the W net of the process, the cycle of 1, 2, 3, 4, 1. So this is W net. This is our MEP. Okay. So that is the diagram. So we try to get the cycle efficiency. So what is the formula that we have to do is to look at again at our this formula. This formula. Okay, we need to get what is the RC and what is the R value. Okay, we try to look at this equation first before we look at the basic formula for the thermal efficiency. So let me get the equation first. We are trying to look at this formula first. So we need the RC and R value. So what is the R value? R value is given as 15. Okay. What is RC? The RC, we need to get what is V3 over V2. Yeah, let's look what we have right here. The value of RC is equal to V3 over V2. And if we look at the process of 2 to 3, what do we have right here in terms of the IGS for a given process? So this is a P2 V2 over T2 equal to P3 V3 over T3. And we know that the pressure is the same. Then from here, we could get what is our value of V3 over V2, which is equal to V3 over V2 is equal to T3 over T2. And in this case, the T3 is given. Now we have to get what is the T2. And then from the relationship between the process of 1 to 2, okay, 1 to 2, from here we could write the T2 is equal to the T1 over the V divided by V K minus 1. Again, this is V1 divided by V2. Please check, guys. Is this right? This one? Betul tak?
Betul. Betul.
Ya. V1 over V2 or V2 over V1? Ya, kan?
V1 over V2.
Okay. Please guys, remember tau, jangan lupa please. So this is 288, 288. This is given as 15. V1 or V2 is the compression ratio, and this is 0.4. So how much is that?
Eight 850.8.
Yes,
850.8.
850.8. Okay. So now we get the T2.
So 850.8.
850.8. Okay. So we get the T2. The T3 is the maximum. So we have right here TRC is equal to the T3 is the maximum temperature, which is 1923. This one you need to get in Celsius. 1923 divided by 850.8. So what is your RC?
2.260.
2.26.
26. 026.
0.
Yes.
Okay. So once you have your RC, then put it right here. So thermal efficiency for diesel cycle is equal to 1 minus 1 divided by 15. 15 power of 0.4 multiplied by RC. RC is 2.26. 1.4 minus 1 divided by K 1.4. RC 2.26 minus 1. Okay, so what is the value? And everything should time by 100, then you get in percentage.
$59.1.
Yeah?
59.1.
Okay, 59.1%. Right? So again, you need to find what is the MEP. Then I just show you how to get the MEP. The MEP is equal to dW net divided by V1 minus V2. Okay, V1 minus V2. So how to get the W net? From the thermal efficiency for diesel is equal to the W net divided by the Q in. The Q in is Q23. You already have this value, right? So you need to solve the Q23. What is Q23? The Q23 is equivalent to Cp T3 minus T2. Okay, you know your Cp value, you know your T3 and T2, then you will get your Q23. Once you have your Q23, you will get your W net. Once you get your W net, then solve for your M, EP, and try to get with the appropriate unit. Okay? So in this case, T3 is given, T2, we have got it. Then you can solve for your MEP. Right? Any question, guys? Tak ada, eh? So as far as the air standard cycle is concerned, so we are going to only to have a look into the two types of air standard cycle, which is the Otto cycle and the diesel cycle. So I would advise you to look, try to list down all the differences between the air standard cycle for diesel and Otto. Apart from that, also look the differences between the actual Otto cycle, which is the petrol engine, and also the diesel cycle, which represent the diesel engine. Please list down, because this is a very famous question to get the differences. Right? Okay, any question? Okay. If there is no question, the next thing that we are going to look, we are going to get, or we have to look at the performance criteria. Okay, performance criteria of a diesel or the SI engine. And before that, when we look at the performance criteria, what we have to do actually is we are going to do testing on the engine. So in order to get the basic parameters, what is called as the performance criteria, we need instrumentation to be attached at the performance test up or setup. So what we have actually usually is we have the engine, and this engine is being coupled to a device called as the Dynamo Meter. Okay, this is the Dynamo Meter. This is the engine. This is the Dynamo Meter. Dynamo Meter. Basically, what is a function of a dynamometer? A dynamometer is to give load to the engine. Okay, to give load to the engine. And how do we give load to a dynamometer so that the engine will sense there are some load given to the dynamometer, what is felt by the engine? Basically, what we do, the very basic type of dynamometer is we are using the hydraulic type. So for a hydraulic type, what we give in the dynamometer is we give water flow, okay, with different pressure. Because we know that for a different pressure, the water will give us a different density. So, and the flow rate, the rate of flow rate, the kilogram per second, the mass flow rate also will give the extra load to the dynamometer, which will be felt by the engine. So this dynamometer is basically, we try to simulate the load as though that if a car, we are driving the car with 1 passenger, 2 passenger, 3 passenger, and etc. We know that when we increase the passenger in the car have to produce more power. Okay, have to produce more power. And sometimes we give a high load to the car, the engine could not take the load. What happened? The engine stalled. the engine stop or the cars will stop. So that is what we do. This is everything got to do with engine testing. What we have from the dynamo meter, okay, if we look at the side view of this dynamo meter basically have a torque arm and we have a spring constant which is being anchored to the floor. And this torque arm usually is the torque that we could have the value of this force which is perpendicular to the center of the dynamo meter. Okay? So if we have this R value, then what we could measure right here is the spring constant. Okay, the spring constant, and the spring constant will give deflection because of the engine. And this will be calculated by using K times X. Let's say the engine is running this way, okay, rotating this way, and the dynamo meter also rotating at the same direction of the engine. So when this is happen, the tendency of this spring is to have a effect of tension. And we have adjustment screw right here, okay, adjustment screw right here. So what we do, when the engine rotates, the arm is going up. When the arm is going up, then what we have to do is to adjust the screw right here in order to bring back the arm as perpendicular to the axis, so that it will be always at horizontal position, because we need to calculate what is F equal to Kx. Then this rotation of the dynamo meter is equivalent to the rotation of the engine, which is N. Okay, which is N. So from this dynamo meter, what we could have is the power. Okay, the power is equal to 2 pi N T, and this should be in kilowatt. Okay, should be in kilowatt. And if this power is being measured through a dynamometer, and this dynamometer, what I have said just now, is to give load to the engine. If we increase the load of the dynamometer, which will be felt by the engine, as though that the dynamometer is trying to break the engine from rotation. Okay, what is being felt by the engine because of the load from the dynamometer, what is felt by the engine as though there is a resistance from the engine to rotate. So it's harder to rotate when the load of the dynamometer is higher, right? So as though that the dynamometer is breaking the engine, okay, the breaking the engine from rotation. That's why this type of power is being called as the brake power. Okay, it's being called as the brake power. And apart from that, from the engine side, if we want to look in terms of the energy input, okay, the energy input to the engine, we usually have to measure the flow rate of the fuel. So what we could have is the measurement of the fuel flow rate. Okay, the measurement of fuel flow rate. And also we could have the measurement of the amount of the air flow rate. Okay, and from these two measurements of fuel and air flow rate, we could represent the ratio of these two as what being called as the air fuel ratio. air-fuel ratio. And this is defined as the m dot of air divided by the m dot of fuel. Okay? As we know that the combustion process, we are going to have the combustion of carbon, which produce CO2, and we have the combustion of hydrogen, which will produce H2O. Okay? You see right here, the carbon, sorry, this is wrong. This is not H right here. Let me rewrite that. The combustion of hydrogen is hydrogen plus oxygen. Then we have H2O. It's not balanced, right? So you have to put 2 right here. If you put 2 right here, this become 4. Okay, this become 4. So this is balanced, carbon, 2 atom of oxygen. So this is H2O. I need here 2. Okay, so if right here 2, this is also 2. Then, sorry, undo. I need to get here as H2O, meaning that I need here 2 hydrogen. Okay, 2 hydrogen. And then I need right here is to be half, okay? So we are not concerned on the balance of the equation. What is important is to look at the amount of oxygen. Okay, this is the amount of oxygen to produce CO2 and the amount of oxygen to produce H2O. If the air is being supplied just enough, okay, if the air is being supplied just enough to combust the amount of carbon and also the amount of hydrogen, then the ratio of this m dot A divided by m dot F is being called as the psychometric Fp ratio. Okay, stoichiometric Fp ratio, psychometric Fp ratio. What is the meaning of that? That is what I mentioned just now. If we are using the amount of air just enough to combust completely all amount of hydrocarbon, which is represented as the fuel, then the Fp ratio is referred as the stoichiometric Fp ratio. And for every fuel, they have their own stoichiometric Fp ratio, because we know that, for example, if gas, we have CH2, we have C2H4, and etc. Same goes for the benzene, which is the most constituent of petrol. So we need to look at the equation of the chemical compound of the fuel. Then we need to get what is the combustion equation. Then we could get what is the stoichiometric Fp ratio. But as far as we are concerned right here, we are going to give you directly. Okay, you don't have to look into the microscopic type of analysis to get the Fp ratio. Usually we are given or we measured the Fp ratio. Okay, we put a device, measure what is m dot F. We put a device, measure what we could have the MA. And from this amount of fuel, we know that the fuel have the energy content. The energy content of fuel usually is given by the HV, where HV is meaning of HV is the heating value. Okay, the heating value. Or sometimes some textbook refer this HV as low calorific value. Okay, the same as heating value. And usually this value is around 40,000 to 45,000 kilojoule over kilogram. Then this is the properties of the fuel, the energy content of the fuel. Right? So meaning that what? Meaning that this value, let's say 40,000 value, this value of energy is being possessed of 1 kilogram of fuel. Okay, this is fuel. If we have 45,000, then meaning that for every 1 kilogram of fuel, we have the energy amount of 45,000 kilojoule over kilogram. So, what we could get from this MF, okay, when we integrate this MF, what we could represent these two value HV and or LCV is the Q supply. Q supply, or known also the Q in to the engine. And this should be derived from the M dot F multiplied by the LCV. Okay, so this is what we have. So basically, what is BP? The BP is actually what we have in terms of the W net. Okay, the W net, or the W output from the engine. Okay, so this is basically what meaning by the performance criteria. But this is basically what we have is all the auxiliary or all the devices which we try to tap at the perimeter or the outside of the engine. We don't touch inside the cylinder. Okay, so from here, basically what we want, we could get what is called as the brake thermal efficiency. Okay, brake thermal efficiency, which is the BP divided by the Q in. If this BP is in kilowatt, then this should be Q dot in. Okay, Q dot in, and this is Q dot. This is Q dot because this is M dot. So this is our formula to get the thermal efficiency. This is the formula to get what is the brake power. Okay, right. So this is what we try to look outside of the engine, whereby we put all the devices or the measurement device outside the engine. Now we are going to look what we can do in terms of the combustion analysis, whereby we try to get the pressure inside the engine, okay, inside the cylinder. So let's us look at one side, okay, at one side of the cylinder, only one cylinder. So you could have here a cylinder, let's say for our petrol engine. There is one device called as the pressure transducer, okay, pressure transducer. And this pressure transducer is basically to measure the pressure inside the cylinder when we have the movement of the piston. Okay, we try to tap the pressure variation when the piston is moving. And this variation of pressure, we are going to get from a pressure transducer, And this pressure transducer is the spark plug type. Okay, what we have right here, we have a spark plug, and inside here we have a piezo crystal, okay, piezo crystal, which it can give spark, and at the same time it could get what is the pressure inside the cylinder. And we try to measure the variation of pressure against the rotation of the crankshaft. Okay, we have, for a 4-stroke engine, we have a crank angle that giving us the total of 270 degree for one cycle. Okay, for one cycle. So we could get for every angle what is the pressure inside by using this pressure transducer. This is our pressure transducer. What I call just now is the spark plug type. Okay, we have a pressure transducer right here. So what we could get here is the P and also the theta value, the angle. For every angle from 1 to 720, we get what is the pressure look like. Okay, and when we plot this pressure against the crank angle theta, what we could get is this type of graph from 0 up to 700 degrees C. Okay, and for this crank angle, right, for this crank angle, what we could convert is the position of this piston. At different angle, the level of this piston movement is different. And we could convert this value of crank angle to what we could get is the volume. Okay? So if we could convert the theta, the angle, to volume, so what we could get right here is actually the PV diagram in terms of this shape. Okay, this is our PV diagram for actual engine. So we could get this PV diagram. So what we want to get is basically is the W net. What is the W net? This area minus this area. Okay, this is called as the indicator diagram. This is called as indicator diagram. And from this indicator diagram, we could get the area of the diagram and also the length of the diagram. Okay, the area of the diagram and the length of the diagram. And also, we could get the spring constant used in order to get this diagram. Okay, from this indicator diagram, we could get the area of the diagram, the length of the diagram, and the spring constant used in order to get the pressure variation. Because in order to get this pressure variation, we need the S value. Okay, so this diagram is called as the indicator diagram. It's basically what we could use, what is being called as the indicator diagram device. Let me have a look if I could show you the indicator diagram. Okay, this is what I have mentioned just now. You see, we have a pressure transducer, and then we could measure the angle for the position, represent the position of the piston, then we could get the pressure against the crank angle. This is the pressure against crank angle diagram, and we could convert that to a pressure against the volume. And when we look at this diagram, so what we could have is the area of this called as the power loop, and the bottom part is called as the pumping loop, and the total, the summation of the pumping loop and also the power loop, that is what we have as the W net. So this is what I showed just now. This is the pressure against the crank angle diagram. Right? And how to get that? By the use of this apparatus. Okay, this apparatus is being used in order to get the diagram. We have a drum right here, and the drum is what we are going to have this diagram. Okay, the indicator diagram. This is diagram. We are putting a paper on the drum, and we have a pointer right here. So this drum is going to rotate to and forth. Okay, basically link at the crankshaft. This is the link. This is the tie, the cable that we are going to link at the shaft, and this is where we are going to take the pressure on the cylinder. In this pressure, this is what we have. We have the spring constant. Okay, the spring constant. And then with the aid of what being called as the planimeter, okay, the planimeter, from the planimeter, we could get what is the area of this indicator diagram, and we could convert the indicator diagram as a rectangle which represent the MEP. Okay, which represent the MEP. So we are not going to measure, right, during the exam, but what we are going to give you is the value of area. And this value of area we are going to have from a device called planimeter. Okay, this is what being called as the planimeter. Which one is planimeter? Where is the planimeter diagram? The apparatus planimeter, just planimeter. Yes, this is a planimeter. We trace the diagram, and the planimeter will give us the A value and also the L value that I have mentioned just now. Right? Okay. So from this A value and L value, the A value is usually in millimeter squared, the M usually in millimeter, and the S is usually in the kilo or kPa over millimeter. So if we have this A times L divided by S, let me put right here, this is meter squared times meter, millimeter, times S is a kPa over millimeter, right? AL over S, AL over S. Oh, sorry, I think I got the wrong formula. AL over S, A over L times S. Okay, sorry guys. If we have A over L times S, A is in millimeter squared, this is in millimeter, multiplied by kPa over millimeter, what we could have right here is the kPa. Okay, with this unit, A as millimeter squared, L as millimeter, and S as kPa over mm. If we get A over L times S, we could get kPa. And this kPa is referred as the indicated pressure. Okay? As indicated pressure. So basically, what we want to get from the engine inside the combustion chamber is the PI. Okay? Basically, what you want is the PI. The amount of pressure developed inside the cylinder. And this PI actually is the mean effective pressure, but inside the cylinder. So this is referred also as the indicated mean effective pressure. Okay? So now we try to look to the text. Whatever haven't been covered in the text, I will try to explain furthermore. Okay. So the indicator diagram is this what we want to have from the indicator diagram. Okay, we tap the pressure transducer, and when we tap the crank angle, this is what we want to get. And when we get the area of this power loop and the pumping loop have negative power. So when we plus that, then we get the W net. Okay, so this is a diagram for the pressure against the volume inside the cylinder. Okay, inside the cylinder. Okay, this is the two-stroke. Then I want to show you the performance criteria. Yeah, this is the performance criteria. So this is what I mentioned just now in terms of indicated power. So what is indicated power? Okay, defined as the rate of work done by the gas on the piston as evaluated from an indicator diagram obtained from the engine. Okay, this is obtained from the engine. And what is the net work? The net work is equal to the area of pumping loop or power loop. This is the area of power loop minus the area of pumping loop. This is for a 4-stroke engine. Okay, a 4-stroke engine. Then when this minus this sum up these two, positive work and negative work, then we get the W net. And then we have the PI. The PI is net area of the diagram divided by the length. This is what I have given just now. This is equal to what? This is equal to A over L times S. The net area of the diagram divided by the length of the diagram. The net area should be this minus this area. Net area divided by the length of the diagram. This is the length of the diagram. Then the time by the constant. What constant? The spring constant. The scale used to record. Okay, the scale used to record. It all depends on the stiffness of the spring. So this is what we have. So from the indicator diagram, we have the PI. Then we can convert the work done per cycle per cylinder as the PI times A times L. What is the A? A is the area of the piston. What is L? S is the stroke of the piston. Okay, the stroke of the piston. So don't get confused. The A, this A and this L. This A, L, small a, small l is from the indicator diagram. This is indicator diagram. But the work done is equal to PI times A times L. The PI is this PI. but the A is the area of the piston and the L is the length of stroke. So from there, we are going to have this formula. Okay. And then from this indicated diagram, if we are only looking at one cylinder just now, okay, we are only looking at one cylinder. So if we have 4 cylinder, 3 cylinder, more than one cylinder, then this is the equation that we are going to use in order to convert from one cylinder per cycle to multiple cylinder per unit or for one speed of the engine. So what is PI? The PI is this PI, the same PI as this. A, area of the piston. L, the stroke of the engine. N is the speed of the engine. And the small n is the number of cylinder. Okay. And then why we have to divide by 2? We have to divide by 2 because this formula is being used for 4-stroke engine. Because we know that the PI is only once for every 2 turns of the crankshaft. Because we have 720 degree to complete one cycle. Okay, 720 degree to complete one cycle. And one cycle for 4-stroke, in the 4 cycle, for one cycle consists of 4 strokes. Okay, 4 strokes. And from these 4 strokes, we only have one PI, which is the power stroke. That's why we need to divide by 2. Right? But for 2-stroke engine, we don't have to divide by 2 because for a 2-stroke engine, every one rotation produce one cycle. Okay, produce one cycle. So what is IP? If I can look again to this diagram, what is actually IP? The IP actually represent by the power produced by each cylinder. IP1, IP2, let's say 4 cylinder, we have IP3 and we have IP4. So what is the IP? If we sum up all the IP, IP1 plus IP2 plus IP3 plus IP4, this is the potential of energy or the power that we could have from the engine. But this is not from the output of the engine. What is actually output from the engine is from this shaft. And the output from the engine usually we refer as the brake power. So now we have 2 types of power. One is the power that represent as in the cylinder, and another power is what is being produced by the engine. Okay? I think I will stop right now and we continue on Wednesday, inshallah. Any question, guys, before I take your attendance? Any question? This is called as part of the performance criteria. Okay, we are basically, I think 90% we have looked what is in the performance criteria already. So that is your attendance, guys. Please sign in. Any question?